today we're going to continue looking at the graphs of the trigonometric functions sine and cosine, and specifically what happens when you start doing transformations to them. Our subject is going to be graphs of functions of the form y equals a times sine bx plus c, or y equals a cosine bx plus c, where a, b, and c are real numbers, and we want to see what this does to the graphs of sine and cosine. This is particularly important for many applications because sine and cosine are very good at describing cyclical types of behavior where some quantity rises and falls in a regular pattern. For instance, they're excellent at approximating things like the temperature in a city over an entire year. It's going to be hot in the summer, then cold in the winter, then hot the next summer, and so forth and so on. It's going to be good at describing the number of hours of daylight in a year, or any other types of cyclical behavior like this. And so it's important for us to understand how we can describe these sorts of things using sine and cosine, and the place to start there is to see how the graphs of sine and cosine change when we introduce constants like the a, b, and c in these places right here. Now, we also are going to want to talk about what happens when we add a constant at the end, a d like this, although nothing new happens here compared to what you're familiar with from previous algebra courses. The first step to understanding the trigonometric graphs of these variations on sine and cosine is to remember what the graphs of sine and cosine themselves look like. And the strategy that we use here is we look at the interval from 0 to 2 pi. And we're starting there because that's one period of sine. That's going to wind up being very important. One period of sine and one period of cosine. And we know that sine and cosine lie between -1 and 1. Once we know that the period goes from 0 to 2 pi, we split up the period into 4 pieces. And so we put a mark in the halfway point of the period and then in the middle of each of the 2 sub-intervals that we've created. And now, if we're looking at sine, all we have to do is remember that we start our period over here at the origin, and then we start by going up to 1 at pi over 2, down to pi, down to -1 at 3 pi over 2, and up to 2 pi, and then we continue on. I'm only going to sketch out one full interval here, but this blue line gives us y equals sine x. Cosine has the same period, and so we're going to mark it the same way. Start by marking the period, and then split it up into the four intervals inside. Cosine, instead of starting at the origin, starts at the point 0, 1. It starts up at the peak, comes down to pi over 2, comes down here to pi, comes up to 3 pi over 2, and then up to 2 pi like this, and then continues on. So here's what y equals cosine x looks like. And so these are where we're starting, and what we're going to do is we're going to build up seeing how introducing each of the numbers a, b, c, and d affects the graph, and that's going to wind up giving us some names that we use to describe these kinds of functions. So first, I want to note that these functions are sometimes called sinusoidal, meaning that they behave like sine. They go up and down in a cyclical rhythmic pattern like this. So we're really studying the graphs of sinusoidal functions here. So let's start with A. So let's look at the graph of y equals a sine x. And the arguments that we use for sine, the examples we use for sine, they're pretty much all going to apply. They are all going to apply to cosine as well. So for the most part, we'll just stick with seeing what happens with sine and briefly touch on cosine. Now, you may remember from algebra that when you multiply a number on the outside of a function, what this does is it multiplies the y values of all points on the graph by a. So let's see how that looks with a bigger graph here. All right, let me mark my points. 0 to 2 pi, pi over 2, 3 pi over 2, 1, -1. For the sake of example, I will start by just graphing out the normal sine function. This isn't a bad strategy, by the way. When you do go to graph these functions, it's often good to just go ahead and graph the basic function that you started with, y equals sine x. And also for the sake of this exercise, I'm going to note the coordinates of each of these points that I've noted on the graph. So 0, 0, pi over 2, comma 1, pi, comma 0, 3 pi over 2, comma -1, and 2 pi, comma 0. And once again, I mentioned that this is just one cycle of the graph. It continues and repeats itself over and over as you move to the left and the right. So now let's look at y equals 3 sine x. What this is going to do is it's going to multiply all y values by 3. Or in other words, this is going to stretch the graph vertically by a factor of 3. So what this means is that we can take every point on the graph, multiply its y value by 3, and get the point on the new graph. So let me go ahead and label the points 3 and -3 here, because those are going to be what we want. So if we multiply the y value of 0, 0 by 3, we still get 0, 0 again. But if we take pi over 2, comma 1, that becomes pi over 2, comma 3. We've multiplied that y value by 3, stretching the graph vertically. The point pi 0 is going to stay the same because 3 times 0 is 0. Then we'll get the point 3 pi over 2, -3, because that's -1 times 3. And then 2 pi 0. And so if we connect these up, we get the following graph, which is an elongated version of the original one. So y equals 3 sine x gets stretched out this way. Now this stretching out has changed what the graph of sine looks like. If we imagine that the sine function is actually describing the motion of something, let's say it's describing the height of the tides in a particular area, then multiplying by 3 means that we've got much more extreme movement of whatever it is that we're measuring. The original function sine only goes between -1 and 1. The function 3 sine x goes from -3 to +3, and so it has much wider variety in the types of numbers that it goes to. It goes to further extremes. If you use this type of function to describe sound waves, then a bigger wave like this results in a louder sound. A louder sound wave corresponds to a taller sine wave when you go to describe it using this type of mechanism. So the distance between the center of where the sine function is oscillating around and the peak, this distance is known as the amplitude. And I'll define this in a second. This is the amplitude. So this function, for instance, the y equals 3 sine x, has an amplitude of 3. The original function, just y equals sine x, has an amplitude of 1. Before we define it, I want to give one more example of one of these types of functions, a sine x. So let's look at the function y equals -1/2 sine x. This is going to work similarly to the first example we did, but instead of multiplying all of the y coordinates by 3, we're going to multiply all the y coordinates by 1/2, or not 1/2, but -1/2. So this is going to do two things. Again, if you remember your general rules from algebra about how functions change when you multiply them by numbers, the 1/2 in front is going to squish the graph. It's going to compress it so that it doesn't go as far up or as far down. And because the multiplication on the outside is negative, that's going to flip the whole thing around the x-axis. But we don't have to remember all that. We just have to remember, what does this do to the y-coordinates? So our y-coordinate of 1 for this first point here, for pi over 2 comma 1, goes to the point pi over 2 comma -1/2, because we're multiplying that y value by -1/2. The point 0, 0 stays the same. The point pi 0 stays the same, but the point -3/2, or sorry, 3 pi over 2, sorry, don't know where that comes from, comma -1 becomes 3 pi over 2 comma 1/2, because 1/2 times -1/2 is +1/2. And then finally we get back around to 2 pi comma 0. So the yellow function, y equals -1/2 comma -1/2 sine theta, gets us this curve. It's flattened. It doesn't go up up or down quite as much. It's a compressed version of the original sine function. So that's what it looks like when we multiply sine by a number in front. The easiest way to handle it is just to take the points from the standard sine function and multiply them by that number on the outside. Now again, we're going to call this distance from the center line of the sine function up to its peak or down to its valley the amplitude. So we say that y equals 3 sine x has amplitude 3, and then y equals -1/2 sine x has amplitude 1/2. The amplitude never measures whether something's been flipped around the x-axis or not. The amplitude is always just a distance, and so it's always positive. a distance from the center line that everything's oscillating around up to the peak, down to the valley. It's a measure of how much waviness do we have, how big are the peaks and troughs of our graph. So we can define this in the following way. The altitude, amplitude of y equals a sine bx plus c plus d and y equals a cosine bx plus c plus d is the absolute value of a. So I want to just briefly mention that, not to get too far ahead of ourselves, but when the d in our expression is non-zero, that means that we'll actually have a curve that does something like this. It'll be a sine type curve, but it won't be centered around the x-axis anymore. It'll have some other center line here. In that case, the amplitude has nothing to do with the actual y values of the graph. The amplitude is still measuring the distance to the center line without making reference to the x-axis. So all these things are still the amplitude of the function. So we will often describe the amplitude of a sinusoidal function, or a problem may ask you for the amplitude of a function, either based on its graph or based on its function. If it's based on the graph, then you measure it in the way illustrated here. Another way to think about the amplitude is that it's half the distance from a peak to a valley. So if I take the full distance, say the difference in the y values between the top of the curve and the bottom of the curve, half of that will be the amplitude. So that's how we handle the graphs of sinusoidal functions when a is something other than 1. Let's look at what happens when b is something other than 1. So now let's consider y equals a sine bx. We're going to continue keeping a little bit different here. It might be 1, it might be something other than 1. We're going to continue working with that. So as you may recall from algebra, when we multiply some number by x, that is going to either compress the function horizontally or expand it horizontally. When we multiply something inside the function, that affects the horizontal movements here. Now, a good way of thinking about what's going on here is the following. We know that sine of x, or let me say sine of theta, makes one full period, one full movement up and down and back in the interval where the theta goes from 0 to 2 pi. So if theta equals bx, then sine of bx makes one full period in the interval defined by 0 is less than or equal to bx is less than or equal to 2 pi. Now, we would want to solve for x here to figure out what's going to happen with the function y. Here we have to be a little bit careful, depending on whether b is positive or negative. So if b is positive, then we can just divide both sides by b, and everything's fine. If b is negative, though, then dividing by b means we have to change the order of the inequalities that we work in. And in this case, 2x over b will be a negative number. So what this means is that in either case, and we'll do an example in a minute where we go through this in more detail, is that whereas the normal sine function does one full period from 0 to 1 to 0 to -1 back to 0 within the interval from 0 to 2 pi, this function, a sine bx, is going to do one full period in the interval from 0 to 2 pi over b, if b is positive, and from 2 pi over b to 0 if b is negative. Now, to actually graph out this function, we're going to do things the same way. We're going to make our three marks inside, and we're still going to take our function, start at 0 and go up to a now, because we're dealing with an a here in front of sine, down to 0, back down to negative a. Here I'm assuming that a is positive, and back up here. And that's basically going to be our process. Now, if b is negative, then we would look at the interval from 0 to 2 pi over b here on the left. We could make our marks, 3 marks, splitting it up into 4 pieces, and continue going with the graph over to the left like this, with the reflection here being based on the fact that when we multiply the x inside a function by a negative number, that flips the graph around the y-axis. So we've got these two different cases here that are reflected on each other, but the point in both cases is that the period of the resulting function is still the same. So the period over here is the total distance from 2 pi over b to 0, which is 2 pi over, well, the absolute value of b. We want the absolute value because the period has to be a positive number. And the same thing here. In this case, on the right, the period is actually 2 pi over b, but of course, because b is positive in this case, we don't lose anything. We're not incorrect if we write the absolute value here either. So this gives us our next fact, or I'll write it as a definition. The period of y equals a sine bx plus c plus d and y equals a cosine bx plus c plus d is 2 pi over the absolute value of b. And the point of the period is that the sine function or the cosine function does one complete cycle of going, in the case of sine, going from the middle to the top, to the middle, to the bottom, back to the middle, in one period. And for cosine, of course, it goes from the top to the middle, to the bottom, to the middle, back up to the top, as one full cycle of cosine does. So let's see a couple of examples. So let's let y be, we'll start with something simple. Let's y equals sine 2x. Let's see how we would graph that out. So the first thing that we'll want to do is identify the amplitude, and the next thing we'll want to do is identify the period. So the amplitude is always equal to the absolute value of a, and a is the coefficient that sits on the outside of the function. Now in this case, there's nothing written there, so a is just the invisible 1, so the amplitude of this function is just 1. So it's going to have a height of 1, it's going to go up by 1 and down by 1 from its middle line. And its period is going to be 2 pi over the absolute value of b. Now the absolute value of b in this case is the absolute value of 2, because b is 2 right here. And so that's 2 pi over 2, which is pi. So that means that the period of this function is pi. Let's graph it out. So now what we want to do is we want to start by noting pi here, and we'll go ahead and give 2 full cycles of this function. So we'll also go to negative pi over on the left. Your next step is always to set up your tick marks between 0 and pi. 0 and whatever your period is. So you get the halfway point, which in this case will be pi over 2. Then you divide that in half again, which is pi over 4. And then halfway between pi over 2 and pi is 3 pi over 4. Next, you'll note the amplitude and the negative of the amplitude. And now we're ready to graph this out. So sine starts at the center of its graph. And then it goes up to its maximum, in this case 1, then down to the center, which is 0 here, and over here to negative 1, and then up to pi. And now the problem often asks us for 2 full cycles. So it's often easy to do that by continuing off to the left, like this. So here's what y equals sine 2x looks like. Now, without comparing it to the original sine function, it's difficult to see what's different because the way we've sketched it out. However, notice that the original sine function, if we do sketch it out here, started at 0 and then hit its peak at pi over 2. And then came back down to 0 at pi. Let me make that look a little bit better. And then continued on like this. So this is what y equals just sine x would look like. So we can see that by going to y equals sine 2x, we've compressed things together. Similarly, if b was a fraction, something like 1/2 x, then the period would actually be larger than 2 pi, and so we'd be taking the original sine function and stretching it out. All right, let's do another example. Let's do an example with a negative value of b, because we do have to be a little bit careful with that. Let's let y equal 4 times sine of negative 1/3 x. Let's see what this graph looks like. Once again, we want to start with the amplitude. And the amplitude in this case will be the absolute value of 4, which is just 4. The period is going to be the 2 pi over the absolute value of negative 1/3, which is 2 pi over 1/3, which, when you simplify that all down, gives you 6 pi. So this function is going to take a distance of 6 pi to complete one complete cycle. So let's start sketching this out. Once again, we want to start with noting the endpoint of our period, 6 pi over here. Halfway to that is 3 pi. And then halfway there is 3 pi over 2. And then 9 pi over 2 in between. But now here's where we have to be a little bit careful with the negatives. And in fact, this would be a good place, again, to keep track of what's going on the left side of the graph as well. So we want to just copy things over from the left to the right. We know that we've got an amplitude of 4, so it's going to go up to 4 and down to -4 here. And now when we start sketching things out, we're going to start at 0 again, but here's where we have to be careful. Because b is negative, we do have to take this into account. If we just forget the negative, we'll have done something wrong. It means one way that we can handle it is we can draw the graph to the left of the origin. In other words, we're going to flip the whole graph around the y-axis, which is what multiplying by a negative inside the function does. So instead of going up like this as our first step, we're going to go up and to the left for our first step and get up here to 4, down here to -3 pi, down to -pi over 2, or down to -4 at -9 pi over 2, and back up to 6 pi. And then we're going to continue the pattern of up and down as we continue through here. So this is what the graph of 4 sine -1/3 x looks like. Now there are some things that you can do to check your work, which is usually a good idea to do, especially when there are negatives running around. It's easy to lose track of things, to not get things quite correct when you're working with negatives. So a good way to check your work is to plug in some value, some x value, corresponding to a peak or valley of the function that you've graphed, to make sure that it matches up with what to make sure that the y value that you get out of the function matches up with the y values that you have on your graph. So you can actually pick any of these peaks or valleys, and it'll help you to determine. I am arbitrarily going to choose 3 pi over 2, and I want to make sure that when I plug 3 pi over 2 into my original function, that I should get -4 out of it, because that's what my graph suggests should happen. So if x is equal to 3 pi over 2, then y is 4 sine -1/3 times 3 pi over 2, which is 4 times sine of, now -1/3 times 3 pi over 2 gives -pi over 2. So now I want to ask, okay, well, what's sine of -pi over 2? So for this, I can think of the unit circle, and I know that as I go to the angle -pi over 2, first of all, I'm moving clockwise around the graph, and I know that pi over 2 is 1/4 of the way around the circle. That means that sine of -pi over 2 is going to correspond to this point on the graph. Now, this point on the unit circle is at the very bottom, and so it has coordinates of 0, -1. That means that sine of -pi over 2 is -1, which gives me -4 out of it, which is what I wanted there. So that checks out. That means that it looks like I probably did everything correctly. If you don't get the right thing out of that, if I had gotten +4 out of this, that would have meant that I'd done something incorrectly in the process and would need to go back and check it out again. All right, before we go on to the next value, to the c in our formula, let's look at an example of how we can go the other way. Start with a graph and find a trig function that matches it. So find a function of the form y equals a sine x, or y equals a sine bx, or y equals a cosine bx with the following graph. So let's say I've got a graph that looks like this. It starts at the origin, goes up to 5, comes down here to -5, gets here, and this point right here is at the coordinate 10 along the x-axis. So when working out these problems, there are a few things that we need to check. The first is to check, are we dealing with a sine or a cosine function? And when we get to the full complexity of how these problems work, it's going to turn out that any sine graph is also a cosine graph with slightly different numbers. But in this case, we're only looking at functions of the form a sine bx or a cosine bx. What that means is that their normal period, their normal 0 to 2 pi period, is going to be from 0 to something, which means that we can tell whether we're looking at sine or cosine by looking at what's happening at 0 when x is 0. So since this graph is starting at the origin, is starting in the middle of our range that the function goes through, that means it's a sine. So sine starts in the middle of the function's range. Cosine starts at an extreme of the range. So it's either, so cosine would start either all the way up here at the top or all the way down here at the bottom. And whether it started at the top or bottom would determine whether your a value was positive or negative, but we'll get to that in a second. This problem has the graph starting in the middle of the range, and therefore we're going to use sine. So in our example, we're going to use that y is equal to a sine bx. So now we want to figure out what a and b are. Well, for that, we're going to use the fact that we can measure the amplitude and the period by looking at the graph. So the next thing we want to do is we want to look at the amplitude of this function. And as I mentioned before, there are two ways we can look at it. We can either measure from the peak or valley of the function to the middle line, the line it's oscillating around. And in that case, we can see that the amplitude is 5. The other way we can do it is by looking at the distance from one of the valleys to one of the peaks in the y direction. In this case, we'll notice that's 10 because it goes from -5 to +5, and then we divide that in half in order to get the amplitude. So it's either just 5 because that's what we observed, or it's 10 divided by 2, which of course is also 5. So what that tells us is that the absolute value of A is 5. And so A is equal to 5 or -5. Well, how do we determine which one it is? This depends on whether we're working with a sine or a cosine function. If we're working with a sine function, what we want to do now is we want to look at whether the function goes up or down as you move from the starting point to the right. If it moves up, that means that A is positive, and if it moves down, it means that A is negative. Remember that if A is negative, that means that we're going to take our normal graph and flip it around the x-axis. And so sine normally, the standard way for sine to go is to start at the origin and then go up. And so if it does that, then that means it hasn't been flipped, A is positive, and if it goes down, that means that it has been flipped, and therefore A is negative. So in our case, we have that the graph goes up the standard direction for sine, so it hasn't been flipped, so A is 5 and not -5. All right, we're 2/3 of the way there. We determined the function, we determined the value of A, so now we need to use B. So we now need to look at the period. Now the period can be obtained by looking at how long it takes to go from one point on the graph to the corresponding point on the graph when it's on its next cycle. So, for instance, if we start here at 0, we can go over, and this point right here is not where we start, is not where we stop, because we started from a point where the graph was at the x-axis, but going up. We haven't gotten there yet. We've gotten to a point where the graph is on the x-axis, but it's going down as we move from left to right. So we continue looking, and we get over here. Now notice that at both 0, at x equals 0, and at x equals 10, the graph is on the x-axis, and it's headed up. And that's an indication that that's where the function has started repeating itself. So the function starts at 0, it goes along its merry way, it goes up to 5, comes down to -5, comes back up to 10, and then it's going to keep doing that whole thing over and over again. But that means that the period of this function is 10. And we also know that 2 pi over b, the absolute value of b, is equal to 10. And therefore, we get that the absolute value of b has to be 2 pi over 10, which is pi over 5. And so then the question again becomes, well, is b equal to pi over 5 or -pi over 5? Well, here's where things are simple. We actually only need to take negatives into account in one place. We either take it into account with the a's or we take it into account with the b's. And we've already checked it for the a's. We already checked to see whether a was positive or a was negative, and since we've done that, we always take the positive value of b. So we always can take b to be positive when we're going through this process here and coming up with some function that has the given graph that we're looking at. So that means that we've determined all the things that we need to know about the graph. We determined that we're using sine, not cosine. Our a value is 5, and our b value is pi over 5. So our answer is y equals 5 sine pi over 5x. All right, let's do one more example, and I'll move through this one a little bit more quickly, but I want to illustrate one more thing. All right, we want to do the same thing, but now our graph looks like this. And let's say we're given the following pieces of information. We're told that this point right here is 6, 3. We're told this point right down here is 14, -3. And let's say that's all we're told. Believe it or not, we still have enough information to figure out to figure out a function that has this graph. So using the same criteria as last time, we want it to be a sine x or a cosine x. Let's work this out here. So first of all, we want to ask sine or cosine. So again, the answer to this is we want to look at the starting point over here, and we want to say, does the graph start at the middle of its oscillation or at one of the two extremes? We can see here that it starts at one of the two extremes. It starts down at the bottom of its oscillation, and therefore it's cosine. So it's cosine since we start at the bottom of the oscillation. And we would also choose cosine if we were starting at the top of the oscillation. We only choose sine if we're starting at the middle. So we've got y is equal to a cosine bx for some a and b, which we're about to figure out. All right, so for the amplitude, on this one, we can look at the maximum and minimum y values that we get out of the function, and we're given coordinates for a peak and a trough here. So in this case, what we can do is take the difference between the maximum y value and the minimum y value and divide by 2. So in this case, we get 6 over 2, which is 3. So there's a distance of 6 between the peak and the valley, and therefore the amplitude is half of that, or 3. So that means that the absolute value of a equals 3, which means that a is 3 or -3. Now, when working with cosine, we determine whether a is positive or negative by looking at whether the graph starts at the top or the bottom of its oscillation. So 3, the positive value, will happen if we start at the top of the oscillation, and -3 will happen if we start at the bottom of oscillation. In this problem, we've started at the bottom of the oscillation, so we're going to use the -3. So a is going to be -3 for us. Now what about the period? In this case, we're only given 2 points here. We're given a peak and a trough, and so we aren't given 2 points that actually lie beg your pardon. We aren't given 2 points that are exactly match up on 2 parts of 2 periods which are exactly the same. Therefore, what we can do is look at the distance from one peak to the next valley, and that is going to be half a period. And I just noticed a typo that I'd written down. Apologies about that. This bottom should be 12 comma negative 3. It doesn't change anything that we've done so far, but it's necessary for what we have next to make sense. So the period is the distance from one peak to the next, but it's also going to be twice the distance from one peak to the next valley. So in this case, the period is going to be 2 times the distance from this peak at 6 comma 3 to this valley at 12 comma negative 3. So it's going to be 2 times the horizontal distance between them, which is 12 minus 6, which is 6. So we get 2 times 6, which is 12. So that means that 2 pi over b, which is the period of the function, is equal to 12, and therefore b is equal to 2 pi over 12, which is pi over 6. Again, we can always take our b to be positive in these problems, and we typically do. So that means that our answer is y equals negative 3 cosine pi over 6 x. And that's the function that will match up with these points, with this graph. One place that you might run into this particular problem here is you might be looking at the tides at a particular location, and you might be measuring them over time. And you might say that at, say, 6 a.m., the tide, the water level was 3 feet higher than normal, than average. And then at noon, at 12 p.m., it was 3 feet lower than average. And then, of course, 6 hours later, it'll be 3 feet higher, and so forth and so on. And so if you were in that situation and you wanted a function that you could plug any time into to find the approximate height of the water relative to the average, then that's what this function would give you. All right, let's look at what happens when we introduce the c in here. So let's look at y equals a sine bx plus c, or y equals a cosine bx plus c. Now, this plus c here is on the inside of the function. It's in there with the x, which means it's going to have an effect on the horizontal placement of the graph. In fact, this c is going to determine a horizontal shift of the graph. So let's look at this the following way. If I've got y equals a sine bx plus c, I know that this has one period on the interval where bx plus c, the inside, goes from 0 to 2 pi. And that's because I know that sine by itself is a function with period 2 pi. And therefore, its normal 0 to 1 to 0 to negative 1 to 0, its normal cycle, happens over the interval from 0 to 2 pi. So that means that it's also going to do that same pattern of 0 to 1 to 0 to negative 1 to 0 again when going from when bx plus c goes from 0 to 2 pi. Now here we can solve for b. So for the moment, let's assume that b is positive. and turns out that what we do will apply even when b is negative. And let's solve for x here. So we're going to start off by subtracting c from both sides. So we get negative c is less than or equal to bx, which is less than or equal to 2 pi minus c. And now we'll divide by b. And what we get is negative c over b is less than or equal to x is less than or equal to 2 pi over b minus c over b. So you'll notice that this is similar to what we got before. So before with c equals 0, we had that x was going between 0 and 2 pi over b. And now what we've done is we've subtracted the value c divided by b from both the upper and lower limit of this interval. This value, negative c over b, is called the phase shift of the function y equals a sine bx plus c. I'll define this explicitly in a second. And the point is the following. What this is going to do to the graph is the following. If I just had the graph y equals a sine bx, then I'd have something like this with a particular altitude, with a particular period. But now, if I take y equals a sine bx plus c, this same single period that was going from 0 to whatever the period of the graph was, is now going to shift, and it's going to shift to start at negative c over b. So in particular, if let's say c and b were positive, so that negative c over b was over here on the left side of the graph, then we would get something like this. So this plus c here is going to have the effect of shifting the graph by negative c over b. So negative c over b means move to the left by c over b. Positive c over b would mean move to the, or if it were a positive number, it would mean move to the right by c over b. So let's do some examples with this. Usually, it's easier, or often I should say, it's easier to just graph out the a sine bx, the graph without the phase shift, first to see where all that is, and then just take that function and shift it to the left or right according to the phase shift. So let's graph y equals, we'll leave the amplitude as 1 this time. In fact, let's go ahead and do y equals sine pi x plus 2. So this time, I'll go ahead and do it in 2 steps, where I'm going to start off by graphing just y equals sine pi x, and then shift it to the left based on the phase shift. So the amplitude of this function is going to be 1. The period is going to be 2 pi over the absolute value of b. b in this problem is pi, and so the period is going to be 2. So if I probably should give myself some room over here. If we graph this out, the period of the function y equals sine pi x is what I'm going to graph first. And I know that it has a period of 2, so I'm going to take my normal 0 to 2 interval, divide it up in my standard way into 4 equal pieces, and then say, okay, I've got a sine function. It's got an amplitude of 1. And the leading coefficient, the leading a, is positive, which means that I'm going to do my normal thing of going up when I leave the origin. So I'm going to go up to 1, I'm going to go down to 0, back down to -1, and back up to 2. And that's one period of my function. So there's y equals sine pi x. But now we need the phase shift. The phase shift is -c over b. So in this case, it's -2 over pi. So what this means is that I need to shift the graph left by 2 over pi. Let me give myself a couple more markings here. -1/2, -1. And so what I want to do is I want to take each of my points on the graph and shift it left by 2 over pi. Now 2 over pi isn't a rational number, but all we really need to get an approximate graph here is to know whether it's less than a half, more than a half, less than 1, less than 3/2, and so forth. So for the sake of the graph, you can plug this into a calculator, for instance. We can say, we can figure out that 2 over pi, well, it's less than 1, but it's greater than a half. So that means that when I shift a point in my graph to the left, it's going to shift by more than a half, but less than 1. So that means that my origin is going to move over here. My first peak is going to move over like this. I'm going to get this point, and this point, and this one right here. So that means that the graph of the full function looks like this. So this is how we can graph a function with a phase shift. Now, if the phase shift turned out to be positive, then we would shift everything to the right. So the formula for phase shift, which includes the -c over b, keeps track of that. All right, last thing, let's look at a graph that involves a phase shift and see if we can work out what a function is that would match that graph. So let's say I want something. Oh, I have an issue there with my line. Let's say I want to go -1/2, 1/2, 3/2, 5/2, and 7/2, and I want a function that does this. So, and let's say that I'm going down here to -2 and up to 2. So we can tell right away that this function has a phase shift, no matter whether it's sine or cosine. And that's because the y-intercept of this graph is neither in the middle of its oscillation, nor at one of the two extremes. If it were based on sine, the y-intercept would be in the middle of its oscillation. If it were based on cosine, it would be at one of the extremes. So, one interesting thing about problems like this is that when phase shifts are possible, the problem has to specify whether it's looking for a sine function or a cosine function, because there are actually ways of describing this graph using both sine and cosine. So let's say we want to find a function of the form y equals a sine bx plus c with this graph. Well, we want to start off the same way as we did before. We want to start off by identifying the amplitude, the period, and we're also going to figure out the phase shift. So the amplitude, in this case, we see that the graph goes down to -2, up to +2. The amplitude of this graph is 2. The period of this graph is going to be given by the following. Or rather, we know the period of this graph. The period of this graph is from -1/2 up to 7/2. So that means that the period of this function is 7/2 minus -1/2, which gives us 8/2, which is 4. So the period of this graph is 4. And then the phase shift, this actually has more than one possible phase shift that we're working with, actually many more. So a normal sine function, which I'll do in green here, starts at 0 and either goes up or goes down depending on whether the a in our function is positive or negative. Which means that in order to get the graph that we have here, we could have started with a function that goes upwards and shifted it to the right in order to get over to this point 3/2 where the graph comes up through the x-axis. Or we could have taken the phase shift of a function that starts off by going down and moving to the left to get to this -1/2. Or we could start with the graph of sine which goes down and shifted it all the way over here to 7/2. And in fact, we could just keep going over and over and over again. In fact, there are infinitely many different phase shifts that could be used to describe this function. And so usually in problems, they will have some way of specifying. Usually, it makes things, it's more commonly done to require that C be positive, meaning which corresponds to a leftward shift of the graph, and we want it to be the smallest C value possible. So usually we shift left as little as possible. Sorry, that sounded wrong. We shift left by as little distance as we can. So we shift to the left, but we do it as little as possible. This is not the only way of doing it, though, and we'll do we'll see an example of that. But in this case, if we do that, we're going to use this shift to the left, meaning that we're going to start with a downward-facing sine function and shift to the left by 1/2. So that means that the phase shift that we're looking at is -1/2, and this also specifies that we want a to be negative in this problem. So in this problem, we aren't using either of the rightward shifts that we've talked about. So with all this information, we can figure out what A, B, and C are. So we have that the amplitude is 2. So we have that the absolute value of A is 2, which means that A is equal to 2 or negative 2. However, our work with the phase shift tells us that we want A to be negative, so A should be negative 2. Now we have that the period is 4, so that means that 2 pi over B is 4. And again, we can always take B to be positive here. So that means that B is 2 pi over 4, which is pi over 2. So there's our B. And then to get the phase shift, once we have B, we have that negative C over B, which is the phase shift, is equal to negative 1/2. But that means that negative C over pi over 2 is equal to negative 1/2. And so multiplying both sides by negative pi over 2, we get that C is equal to pi over 4. Just unwinding that algebra there. And now we've answered the question. So now we've got that a graph of the function as described is y equals negative 2 sine pi over 2x plus pi over 4. All right, so the next thing I want to do is to note that we could also have done this problem using cosine. And so let me copy this figure, go to another page, and we'll do the same problem but with cosine. And also I'm going to drop our restriction on shifting to the left. We're not going to shift to the left in this case. We're going to shift to the right. So now we want y equals a cosine bx plus c. We have a lot of the same stuff. We have that the amplitude is 2, the period is 4, but the phase shift is going to depend on where exactly we shift to. So cosine normally starts up here. Cosine would normally start at the top of the oscillation and come down from there. Now, depending on how we want to shift it, we could work with a cosine that's based either down here at this valley, which would involve a negative value of a because we flipped everything over the x-axis, or over here at 5/2. Let's go ahead and do the 5/2 this time. So for my phase shift, I want to use 5/2. So that corresponds to this phase shift here, where we're taking a cosine function that sits up at 2 on the y-axis and then shifting it to the right until it gets to where we want on the graph. So, and this phase shift, this association of the phase shift means that we want a to be positive because we're keeping the positive form of cosine, of the graph of cosine in there. So this means that a is going to be 2, not negative 2, because a is positive. We have that 2 pi over b is 4. And so in fact pi b is going to be pi over 2 again. So the period, the b value actually stays the same for sine or cosine. The a can differ by a sign. It could be positive in one and negative in the other, as we've seen here. And the phase shift is always different. Now for the phase shift, we have that negative c over b is equal to 5/2. So that means that negative c over pi over 2 is equal to 5/2. And again, unwinding the algebra, this tells us that c is equal to negative 5 pi over 4. So here's our A, here's our B, here's our C. And so another possible answer to this problem is y equals 2 cosine pi over 2 x minus 5 pi over 4. So we've got two different ways. In fact, there are infinitely many ways of describing this one curve using sines and cosines with appropriate phase shifts and so forth. Pay close attention to problems involving this on the homework. They will give you explicit instructions on which phase shift to use in order to make sure that there's a unique answer to the question.